Let's begin with an introduction to NumPy arrays. NumPy arrays are the fundamental data structure in NumPy for numerical computing. They are more efficient than Python lists for numerical operations and can be one-dimensional, two-dimensional, or multi-dimensional. Arrays are homogeneous, meaning all elements must be of the same data type, which allows for efficient storage and operations. Let's start with basic array creation. The first problem asks us to create a one-dimensional array containing numbers from 0 to 9. We use NumPy's array function, similar to Python's range, but it returns a NumPy array instead of a list. The code is simple. Import NumPy as np. Then r equals np, array 10. This creates an array with numbers 0 through 9. Next, we create a 3 by 3 array of all true values. We use NumPy's full function, which creates an array filled with a specific value. The first argument is the shape 3 by 3 in this case. The second argument is the fill value, true. We also specify the data type as Boolean. This is useful when we need to initialize a Boolean array for masking operations. Now let's look at array operations. Problem 3 demonstrates how to extract all odd numbers from an array. We use Boolean indexing, a powerful feature in NumPy. The expression r modulo 2 equals 1 creates a Boolean mask that is true for odd numbers. When we use this mask to index the array, we get only the elements where the condition is true. This gives us all odd numbers in the array. Problem 4 shows how to modify array elements based on a condition. Here we replace all odd numbers with -1. We use the same Boolean mask from problem 3, but this time on the left side of an assignment. This is called Boolean assignment. The syntax is intuitive. We select all elements that are odd and assign them the value -1. The original array is modified in place. Finally, problem 5 demonstrates array reshaping. We convert a one-dimensional array with 10 elements into a two-dimensional array with 2 rows. The reshape method takes the desired shape as arguments. The special value -1 tells NumPy to automatically calculate the appropriate size for that dimension. Here, with 2 rows and -1 for columns, NumPy calculates 5 columns automatically. Reshaping is a common operation when preparing data for machine learning algorithms. These examples demonstrate fundamental NumPy array operations including creation, indexing, modification, and reshaping. Mastering these basics is essential for efficient numerical computing with Python. NumPy's array operations form the foundation for more advanced scientific computing libraries like SciPy, Pandas, and machine learning frameworks. Let's begin with basic array mathematics. First, we'll compute the sum of all elements in an array. We use NumPy's sum function, which takes an array as input and returns the sum of all its elements. For the array 1, 2, 3, 4, 5, the total sum is 15. This operation is fundamental for many statistical calculations. Next, we'll compute column means in a 2D array. The mean function with axis equals 0 calculates the average down each column. For our 2 by 3 array, the column means are 2.5, 3.5, and 4.5. The axis parameter is crucial. Axis 0 means operation along columns, while axis 1 would be along rows. Now let's compute row standard deviations. Using NumPy's std function with axis equals 1 calculates the standard deviation across each row. Both rows in our array have the same standard deviation of approximately 0.816. Standard deviation measures how spread out the numbers are from the mean. This is a key operation in statistical analysis of data. The dot product is a fundamental linear algebra operation. For vectors 1, 2, 3, and 4, 5, 6, it's calculated as 1 times 4 plus 2 times 5 plus 3 times 6, which equals 32. NumPy's dot function performs this operation efficiently. Dot products are essential for many machine learning algorithms and physics simulations. Finally, element-wise addition. NumPy arrays support direct mathematical operations. Adding two arrays with the plus operator performs element-wise addition. 1, 2, 3, plus 4, 5, 6, gives 5, 7, 9. This broadcasting capability makes NumPy code concise and readable compared to explicit loops. These examples showcase NumPy's powerful mathematical capabilities, including aggregation functions, statistical operations, linear algebra, and element-wise operations. Mastering these fundamental operations is crucial for scientific computing and data analysis with Python. Let's explore array manipulation in NumPy. First, vertical stacking combines arrays row-wise. Using vstack on arrays 1, 2, 3, and 4, 5, 6 creates a 2D array with the first array is the first row and the second array is the second row. This is useful when combining data samples with the same features. Horizontal stacking combines arrays column-wise. H-stack concatenates the arrays horizontally, creating a longer 1D array. The same arrays now become 1, 2, 3, 4, 5, 6. This operation is useful when combining different features for the same samples. Array splitting divides an array into multiple sub-arrays. The split function takes the array and the number of splits. Our 9-element array divides neatly into 3 equal parts of 3 elements each. This operation is particularly useful for creating train test splits in machine learning. Reversing array elements is a common operation. To reverse rows in a 2D array, we use slice notation with r-1. This keeps columns intact but reverses the row order. The first row becomes last, and vice versa. This operation is often used in image processing when flipping images vertically. To reverse columns while keeping row order, we use r-1. The colon preserves all rows, while -1 reverses the column order. This is equivalent to flipping an image horizontally. Understanding array slicing is crucial for efficient array manipulation in NumPy. These examples showcase NumPy's powerful array manipulation capabilities, including stacking, splitting, and reversing arrays. Mastering these operations enables efficient data preprocessing and transformation, which are essential steps in data analysis and machine learning workflows. Let's start with basic random number generation. The first problem involves creating random floating point numbers between 0 and 1. This is one of the most common operations in simulations and probabilistic algorithms. The numbers are uniformly distributed, meaning every value in this range has equal probability. We use NumPy's rand function, which generates an array of given size with random floats. The output shows 5 numbers between 0 and 1. Remember, these values will change each time you run the code, as they are randomly generated. This function is widely used for initializing weights in neural networks and Monte Carlo simulations. Next, we generate random integers within a specific range. The randint function takes a lower bound, inclusive, and upper bound, exclusive. So we use 11 to include 10. We generate 10 integers between 5 and 10. This is useful for simulations, games, and random sampling applications. Array shuffling randomly reorders elements. The shuffle function operates in place, meaning it modifies the original array rather than returning a new one. This is particularly important in machine learning for shuffling training data before each epoch. Notice how the original order 1, 2, 3, 4, 5 is randomly permuted. Now we generate numbers from a normal Gaussian distribution with mean 0 and standard deviation 1. The normal distribution is fundamental in statistics and appears everywhere in nature. We generate 100 samples but only show the first 5. These numbers cluster around the mean with fewer values in the tails. Finally, we sample from a binomial distribution representing 10 trials with success probability 0.5. This models events like coin flips. Each output number represents successes in 10 trials. We generate 100 such samples but show only the first 5. Binomial distributions are fundamental in probability theory and hypothesis testing. We've covered essential random number generation techniques in NumPy: uniform floats, random integers, array shuffling, normal distributions, and binomial distributions. These are the building blocks for simulations, probabilistic algorithms, and statistical analysis in scientific computing. Let's explore Boolean indexing in NumPy. First, we select elements greater than 0.5 from an array. The expression r greater than 0.5 creates a Boolean mask. An r mask returns only elements where the mask is true. This is a fundamental operation for filtering data in scientific computing. Next, we replace negative values with 0 using Boolean assignment. The expression r less than 0 creates a mask identifying negative elements. When we assign 0 to these positions, only the negative values are replaced. This is commonly used for data cleaning and thresholding operations. For 2D arrays, we can select rows based on column conditions. Here, r0 greater than 0.5 checks the first column, and we use this mask to select entire rows. This technique is extremely useful for filtering tabular data where you want to select records based on specific column values. Combining conditions allows for range-based selection. The mask r greater than 0.2 and r less than 0.8 selects elements in the open interval between 0.2 and 0.8. Note the parentheses around each condition. They're required because of Python's operator precedence rules. This is how we implement between conditions in NumPy. Finally, we demonstrate advanced indexing by setting random elements to none, not a number. We generate random row and column indices. then assign none to those positions. This simulates missing data in real-world datasets. None handling is crucial in data preprocessing pipelines. These examples demonstrate the power of Boolean indexing for data selection and manipulation. We've covered filtering, data cleaning, range selection, and handling missing data. Mastering these techniques is essential for effective data analysis with NumPy. NumPy allows selecting multiple elements at once using a list of indices. This is more efficient than looping through indices individually. We'll select elements at positions 1, 3, and 4 from an array. From array 10, 20, 30, 40, 50. Selecting indices 1, 3, 4 gives us 20, 40, 50. This direct indexing is fundamental for extracting specific values without modifying the original array. Boolean indexing is powerful for filtering data. Here we have a data matrix and corresponding labels. We'll select all rows where the label equals 1. This pattern is common in machine learning for splitting datasets. We can combine conditions using bitwise operators. This example selects values greater than 2 and less than 5. Note we use an instead of and, with parentheses around each condition. This is crucial for NumPy arrays. The step parameter in slicing 2 selects every second element. This is useful for downsampling data or creating subsets. The syntax is start, stop, step, where we can omit start and stop. To select columns in 2D arrays, we use comma-separated indexing. The colon means all rows, and -1 means last column. This syntax extends to more dimensions for higher dimensional arrays. These indexing methods form the foundation of efficient data manipulation in NumPy. Mastering them allows you to extract precisely the data you need with concise, readable code. Each technique has specific use cases from data cleaning to machine learning preprocessing. Let's begin with cumulative sums, which are running totals of array elements. Each element in the result is the sum of all elements up to that position. This operation is fundamental in time series analysis and probability calculations. Using NP, sum on 1, 2, 3, 4, 5. We get 1, 3, 6, 10, 15. Notice how each number is the sum of all previous elements. This operation is useful for computing running averages and cumulative distribution functions. The diff function calculates discrete differences between consecutive elements. For input 1, 3, 6, 10, 15, we get 2, 3, 4, 5. This is useful for calculating derivatives in numerical analysis and detecting changes in time series data. The unique function removes duplicates and sorts the result. From 1, 2, 2, 3, 4, 4, 5. We get 1, 2, 3, 4, 5. This is essential for data cleaning and finding distinct categories in datasets. Sorting along rows. Axis equals 1. Sorts each row independently. Our input 3, 1, 2, 6, 4, 5 becomes 1, 2, 3, 4, 5, 6. Row-wise sorting is useful for maintaining relationships between columns while ordering values within each row. Column-wise sorting. Axis equals 0. Maintains row relationships while ordering each column. For our array, columns are already in order, so the output matches the input. Column sorting is crucial for organizing tabular data by specific features. These advanced operations provide powerful tools for data analysis. We've covered cumulative calculations, discrete differences, duplicate removal, and multidimensional sorting, all essential for efficient numerical computing with NumPy. Let's begin with matrix multiplication, a fundamental linear algebra operation. When multiplying two matrices, the number of columns in the first matrix must equal the number of rows in the second matrix. Here we multiply a 3 by 4 matrix with a 4 by 5 matrix, which will result in a 3 by 5 matrix. The NumPy matmul function performs this operation. We generate random matrices of the required dimensions and multiply them. The output shape confirms our matrix multiplication worked correctly. We get a 3 by 5 matrix as expected. Matrix multiplication is essential for transformations in graphics and deep learning. The determinant is a scalar value that indicates whether a matrix is invertible and its scaling factor. For our 2 by 2 matrix, 2, 1, 1, 3, the determinant is exactly 5. Though we see floating point representation in the output, non-zero determinants mean the matrix is invertible. Eigen decomposition reveals a matrix's fundamental properties. Eigenvalues represent scaling factors, while eigenvectors show the corresponding directions that remain unchanged under transformation. Our matrix has eigenvalues 1.38 and 3.62, with corresponding eigenvectors. This is crucial for principal component analysis and stability analysis. Solving linear systems is a common task. For equations 2x plus y equals 4 and x plus 3y equals 5, NumPy's solve function finds the solution x equals 1.4, y equals 1.2. This is much more efficient than manual calculation, especially for large systems. The matrix inverse is used to solve equations and compute transformations. For our matrix, the inverse exists because the determinant is non-zero. The inv function returns a new matrix that when multiplied by the original yields the identity matrix. Inverses are fundamental in least squares problems and coordinate transformations. We've covered essential linear algebra operations, matrix multiplication, determinants, eigenvalues and vectors, solving linear systems, and matrix inversion. These form the computational backbone of scientific computing, machine learning, and computer graphics. The Kronecker product is a matrix operation that creates a block matrix from two matrices. It's useful in quantum computing, signal processing, and solving matrix equations. We'll compute it for two 2 by 2 matrices. For matrices A equals 1, 2, 3, 4, and B equals 0, 5, 6, 7. The Kronecker product replaces each element of A with that element multiplied by B. The result is a 4 by 4 block matrix combining all possible products. The conjugate gradient method efficiently solves large Sparse systems for our diagonal matrix A equals diag 1, 2, 3 and B equals 1, 1, 1. The solution X contains reciprocals of A's diagonal, exactly what we expect. The pseudo-inverse generalizes matrix inversion to non-square matrices. For a random 3x2 matrix A, PINV, A gives a 2x3 matrix that best solves the least squares problem, even when exact solutions don't exist. SVD decomposes any matrix into orthogonal matrices U in V(T) and a diagonal matrix of singular values. For a random 4x5 matrix, we get U, 4x4, singular values, length 4, and V(T), 5x5. The singular values reveal the matrix's effective rank. Kolsky decomposition factors a symmetric positive definite matrix into LL(T), where L is lower triangular. Our 3x3 matrix decomposes into this triangular form, useful for efficient solving and sampling. These linear algebra operations form the computational backbone of scientific computing. From matrix factorizations to specialized products, they enable efficient solutions to complex problems in physics, engineering, and data science. Let's start with finding polynomial roots, the x values where the polynomial equals 0. For quadratic equations like x squared minus 4x plus 3, roots can be found analytically. But NumPy's roots function works for any degree polynomial. The roots function takes coefficients from highest to lowest degree. For 1, minus 4, 3, representing x squared minus 4x plus 3, it finds roots at x equals 3 and x equals 1. These are the points where the parabola crosses the x-axis. Polyval evaluates polynomials at specific points. We provide coefficients 1, 2, 3, 4, representing x cubed plus 2x squared plus 3x plus 4, and evaluate at x equals 2. The calculation follows Horner's method for efficient computation. Polyfit performs least squares polynomial fitting. Given x and y data points, it finds coefficients that best fit a polynomial of specified degree. Here we fit a quadratic, degree 2, polynomial to perfectly quadratic data. The Poly1D class creates polynomial objects with useful methods. Deriv computes the derivative for x cubed plus 2x squared plus 3x plus 4. We get 3x squared plus 4x plus 3. This is essential for finding rates of change and optimization problems. Integ computes the antiderivative for our polynomial. The integral is 0.25x to the power of 4 plus 0.6667 x cubed plus 1.5x squared plus 4x plus a constant. Integration is fundamental for calculating areas and solving differential equations. NumPy provides a complete polynomial toolkit, from basic evaluation to calculus operations. These functions are optimized for numerical stability and performance. Whether you are solving equations or modeling data, these tools form the foundation for scientific computing with polynomials. Let's start with future value, one of the most fundamental financial calculations. This tells us how much an investment will grow over time with compound interest we'll calculate. What $1,000 today becomes after 10 years at 5% annual interest. Using NumPy_financials FV function. We input the rate, 5%, periods, 10 years, payment, 0 since we are not adding more, and present value, minus 1,000 as cash outflow. The result shows our $1,000 grows to $1,628.89, the power of compounding. Present value does the opposite, it discounts future money to today's value. Here we find what $1,000 received 5 years from now is worth today at 3% discount rate. The negative sign indicates this is a cash outflow if you're buying this future value. The PMT function calculates loan payments. Notice we convert annual rate to monthly, 5%, 12, and years to months, 5*12. The negative result means this is money you pay out each month. $188.71 monthly pays off $10,000 in 5 years at 5% April. NPV evaluates investment profitability by discounting all future cash flows. Our example spends $100 initially, then receives $20, $30, $40, $50 over 4 years. At 5% discount rate, the NPV is $21.94, a good investment since it's positive. IRR is the discount rate that makes NPV 0, effectively the investment's return rate. Our cash flows yield 12.82% IRR. Meaning this investment performs like putting money in an account earning 12.82% annually. Investors compare this to their required return. These financial functions form the core of quantitative finance in Python. From basic compound interest to sophisticated investment analysis, NumPy_financial provides the tools professionals use daily. Remember, positive values represent cash inflows. Negative are outflows. Structured arrays allow storing heterogeneous data with named fields, similar to a database table. First, we define a data type with field names and types. Then create an array with this structure. This is NumPy's way to handle tabular data without using pandas. We define a D-type with 2 fields. Name, as Unicode string of length 10. And age, as 4-byte integer. The array stores records of people with their names and ages. Notice how we can access fields by name rather than just by position like regular arrays. Sorting structured arrays works differently than regular arrays. We can specify which field to sort by. Here we sort our people array by age in ascending order. The result shows Charlie first as he's youngest. We can filter structured arrays using Boolean indexing on fields. First we create a mask for ages over 25. Then apply it to select matching records. And finally access just the names field. This chained indexing is powerful for data queries. Numerical operations can be performed on individual fields. Here we calculate the average age by accessing the age field directly. This field-based computation is efficient and readable. We can extend structured arrays with new fields using append_fields from numpy.lib. REC functions. Here we add height measurements to our people records. Note this creates a new array rather than modifying in place. As NumPy arrays have fixed D-types. Structured arrays provide NumPy's native solution for tabular data, with field-based access and operations. while Pandas data frames are more feature-rich for data analysis. Structured arrays offer better performance and tighter integration with NumPy's core functionality. They're particularly useful for memory-efficient storage of mixed data types. Let's begin with moving averages. A fundamental smoothing technique. A moving average replaces each point with the average of its neighbors, reducing noise while preserving trends. We'll implement this using convolution. Using NP, convolve with a uniform window. We smooth 1, 2, 3, 4, 5, 6, 2, 2, 3, 4, 5. The valid mode ensures we only compute where the window fits completely. Each output point is the average of 3 consecutive inputs. Cumulative products show growth factors over time. For 1, 2, 3, 4, 5. Each output element multiplies all previous inputs. This grows factorially, useful for compounding scenarios. Window functions like Hamming reduce spectral leakage in signal processing. The Hamming window tapers signal edges smoothly to 0. We multiply our random signal pointwise with this window. Rolling statistics reveal local volatility. Our implementation uses convolution to efficiently compute windowed variance as x squared, x squared. This shows how much values deviate from their local mean. Exponential moving averages weight recent data more heavily. With alpha equals 0.3. Each output is 30% new value plus 70% previous average. This reacts faster to changes than simple moving averages. These window operations form the toolkit for time series analysis. From simple smoothing to advanced spectral processing, they help extract meaningful patterns from noisy data. Each has trade-offs between responsiveness and noise rejection. Let's explore NumPy's statistical operations. First, finding column maximums using np.max with axis equals 0 computes the maximum down each column. For our 2 by 3 array, this gives 4, 5, 6. The axis parameter is crucial. Axis 0 means column-wise operation in NumPy. Next, we find the position of the maximum value using argmax. For array 1, 5, 3, 9, 2. The maximum 9 is at position 3. Remember, Python uses zero-based indexing, so position 3 is actually the fourth element. Argmax is particularly useful in machine learning to find predicted class labels. Now computing row medians. With axis equals 1. NP, median calculates across each row. Medians are robust to outliers compared to means. For our array, the row medians are 2 and 5. Notice the float d type in the output. NumPy returns floats for median operations by default. Correlation matrices reveal relationships between variables. With rover equals false, we compute correlations between columns. Our perfect correlation of 1 occurs because the columns are linearly dependent. In real data, correlations typically range between -1 and 1. This is fundamental for feature selection. Finally, counting positive values per column. The expression r greater than 0 creates a Boolean mask. And summing along axis equals 0 counts true values. 1 in binary, per column. This technique is versatile. You can count any condition by changing the comparison operator. Essential for data quality checks. We've covered fundamental statistical operations, finding extremes with max and argmax, robust central tendency with median, relationship analysis through correlation, and conditional counting. These form the foundation for exploratory data analysis in NumPy. First, let's count missing values. In real-world data, we often have none, not a number, values. Counting them helps understand data quality. We'll use NP, ISNA, to detect nans and some. To count them, for array 1, nan, 3, 4, 5, nan, we count nan per column. The result, 0, 1, 1, shows no nan in first column, 1 in second and third columns. This helps identify columns needing cleaning. A common approach is replacing missing values with column means. We use NP, nonmean, which ignores nans when calculating means. This preserves data distribution while handling missing values. Sometimes we remove incomplete rows entirely. Using any, access equals 1, with ISNA, identifies rows with nans. The tilde inverts this to select complete rows only. This approach is simple but loses data. Boolean masks are powerful for selective operations. Here we create a mask identifying valid, non-nan values. The output shows true for numbers and false for nans. Masks enable conditional operations on arrays. For ordered data, interpolation estimates missing values. NP, interp creates a linear interpolation between known points. From 1, nan, 3, nan, 5, we get 1, 2, 3, 4, 5. This maintains data trends better than simple replacement. Handling missing data is crucial for real-world analysis. We've covered detection, basic imputation, complete case analysis, masking, and interpolation. Each method has trade-offs between data preservation and making assumptions about missing values. Brownian motion is the fundamental continuous time stochastic process. We'll simulate it by accumulating normally distributed increments. Each step is scaled by the square root of the time increment, preserving the process's mathematical properties. The simulation shows the first 10 points of a 1000-step Brownian path. Notice the random but continuous nature of the trajectory. This process models everything from particle movement to stock prices. Geometric Brownian motion models exponential growth with random fluctuations. It's the foundation of the Black-Scholes model in finance. We simulate it by exponentiating a drifted Brownian motion, ensuring prices stay positive while capturing market volatility. The Poisson process models random events occurring continuously and independently. We generate it using exponential inter-arrival times. The rate parameter lambda controls the average number of events per unit time. This process models everything from radioactive decay to customer arrivals. Markov chains model systems where the next state depends only on the current state. Our example has two states with transition probabilities defined in matrix P. The chain starts in state 0 and evolves according to the transition rules. This models everything from weather patterns to board games. The Ornstein-Uhlenbeck process models mean reverting behavior. It's a modification of Brownian motion that drifts toward a long-term mean. The theta parameter controls how strongly it reverts to the mean. This models interest rates, volatility, and other equilibrium systems. These stochastic processes form the mathematical foundation for modeling randomness in continuous time and discrete events. From physics to finance, they enable realistic simulations of complex, unpredictable systems. Mastering them opens doors to quantitative analysis across many domains. The Fourier transform decomposes a signal into its frequency components. We'll analyze a 5 Hz sine wave and use FFT to identify its dominant frequency. This is fundamental for spectral analysis across many domains. For our 5 Hz sine wave sampled at 200 points, the FFT correctly identifies the normalized frequency of 0.025. 5 Hz relative to Nyquist frequency. The magnitude spectrum would show a clear peak at this frequency. Butterworth filters provide maximally flat frequency response in the passband. Our fourth-order low-pass filter with cutoff at 0.1 times Nyquist smooths random noise. The filtr method applies the filter twice for zero-phase distortion. Spectrograms show how frequency content evolves over time. Our signal contains 50 Hz and 120 Hz components. The output shape, 129 frequency bins times 4 time frames, reveals how the STFT divides the 1000 sample signal into overlapping segments. Cross-correlation measures similarity between signals at different lags. We created a delayed version of a random signal, shifted by 5 samples, and correctly identified this lag from the correlation peak position. The Hilbert transform creates an analytic signal whose magnitude gives the instantaneous amplitude. For our sine wave, this correctly returns values near 1.0, plus some numerical artifacts at the edges. These signal processing techniques form the foundation for working with time series data. From frequency analysis to noise reduction and feature extraction, they enable sophisticated analysis of signals across science and engineering applications. Linear programming optimizes a linear objective function subject to linear constraints. We'll minimize x1 to 2x2 with constraints x1 plus x2 is less than or equal to 5 and 2 by 1 plus x2 is less than or equal to 8. The simplex method efficiently navigates the feasible region's vertices. The solution, 0, 5. Means we should produce 0 of item 1 and 5 of item 2 to maximize profit. Equivalent to minimizing the negative profit. This vertex solution is characteristic of linear programming problems. The Rosenbrock function is a classic test problem with a narrow curved valley. Our BFGS quasi-Newton method successfully finds the global minimum at 1, 1, 1, 1, 1, demonstrating gradient-based optimization on a challenging non-convex function. We minimize x squared plus y squared subject to x plus y equals 1. The solution, 0.5, 0.5, lies exactly on the constraint line, showing how optimization handles equality constraints through methods like Lagrange multipliers. Basin hopping combines global exploration with local minimization to escape local optima. Our cosine-based objective function has multiple minima, but the algorithm reliably finds a near-optimal solution. Integer programming adds discrete decision variables to linear programming. Our MILP solver finds the same solution as the continuous case, but guarantees integer values, crucial for problems like production planning where fractional solutions are meaningless. These optimization methods form the computational backbone of decision-making across science and industry. From simple linear problems to complex mixed integer systems, they enable finding optimal solutions in constrained environments. Let's start with basic parallel processing using Python's multiprocessing. We'll split a large array into chunks and process them simultaneously across CPU cores. This approach is ideal for embarrassingly parallel operations like element-wise transformations. The code creates a pool of 4 workers, splits the array into 4 chunks, and squares each element in parallel. Notice the careful handling of keyboard interrupt for proper cleanup, crucial for production code. The first 10 squared numbers confirm correct parallel execution. NumExpr optimizes array expressions by compiling them and using multiple cores. Our example computes 2*a plus 3*b for million element arrays. The key advantage? It avoids temporary arrays and automatically parallelizes the computation. The first 5 results show the weighted sum operation working correctly. Joblib provides high-level parallelization for Python functions. We square 1 million numbers using 4 cores with minimal code changes. The delayed decorator marks functions for parallel execution, while n_jobs controls core usage. The printed execution time shows the speedup compared to sequential processing. NumPy compiles Python to machine code using LLVM. Our Monte Carlo Pi estimation benefits from both compilation and automatic parallelization. The @ngep decorator enables these optimizations. With 1 million samples, we get pi approximately equals 3.1419, demonstrating both accuracy and speed from just-in-time compilation. Dask enables parallel computing on datasets larger than memory. We create a 75,000 times 75,000 array, 56 GB uncompressed, in chunks that fit in RAM. The computation symmetrizes the matrix and computes column means, all while carefully managing memory usage. The first 5 means demonstrate successful distributed computation. These techniques demonstrate Python's powerful parallel computing ecosystem. From multi-core processing to out-of-core computation, they enable high-performance numerical computing while maintaining Python's simplicity. Choose the right tool based on your problem size and hardware constraints. K-means is a fundamental unsupervised learning algorithm for clustering. It partitions data into K-clusters by minimizing within-cluster variance. The algorithm iteratively assigns points to nearest centroids and updates centroids. Our implementation randomly initializes centroids, then alternates between 1. Assigning points to nearest centroid 2. Updating centroids as cluster means the output shows final centroids for 3 clusters on 2D random data. PCA reduces dimensionality by projecting data onto orthogonal axes of maximum variance. Our implementation centers the data, computes covariance matrix, finds eigenvectors, and projects onto top components. Linear regression models relationships using linear combinations of features. We solve the normal equations. X(x), xy for optimal weights. The implementation adds a bias term and recovers near true coefficients despite added noise. Logistic regression models binary probabilities using the sigmoid function. Our implementation uses gradient descent to minimize cross-entropy loss. The coefficients show how each feature affects the classification boundary for our synthetic dataset. Softmax regression generalizes logistic regression to multiple classes. We use the softmax function to output class probabilities in cross-entropy loss for gradient descent. The weight matrix shape, features plus 1 times classes, shows parameters for our 3-class problem. These implementations demonstrate core machine learning algorithms using just NumPy. Understanding them builds intuition for more complex models. Each captures essential patterns, clusters, directions, trends, and boundaries that form the basis of modern AI systems. I hope you found this video helpful. If you enjoyed it, please give it a thumbs up, subscribe to the channel, leave a comment, and share it with your friends. Your support means a lot. See you in the next video.